So far in this series, we have learned about prompts for directly interacting with language models. We also learned about retrieval augmented generation technique, where we provide enterprise data as input context to the model for improving the factual grounding of model's response. But practical enterprise AI applications are more complex than a retrieval followed by an LLM call. They involve coordination of multiple steps to implement complex business logic. And this is where workflows come in. A workflow orchestrates multiple AI and non AI steps to solve complex business problems reliably. Workflows are built on top of prompts and retrieval augmented generation for enabling enterprise grade AI applications. A generative AI workflow is designed by breaking the business problem into structured steps that can be executed and monitored independently, just as a distributed application. Workflow acts as the orchestration layer across the multi step business process, and it coordinates the calls to large language model, which is used for content generation and reasoning, invoke tools such as enterprise APIs, functions, services, databases to retrieve information and execute actions, maintain a shared state so that multiple steps can coordinate with each other to achieve the end goal, and implement safety and reliability guardrails to enforce policies and ensure compliance throughout the workflow. These guardrails can validate inputs, outputs, protect sensitive data, block any action which is not allowed by policy, etc. Let us look at some common building blocks of a general workflow. Every workflow starts with a trigger, an event such as user request, API call, or a scheduled job. Workflows maintain state, which contains information that has been collected, such as intermediate results, context, and its current progress in the process. Workflow executes a series of tasks. Task is a unit of work such as calling a large language model, retrieving documents, invoking API, etc. A workflow may also need a conditional branch where it makes a decision based on the current state or output of the previous step. Independent tasks in a workflow are often executed in parallel, improving the overall performance. Workflows include fallbacks to retry, choose an alternate path, or recover gracefully when something doesn't go as planned. And finally, important information is persisted so that workflows can recover from any interruptions and provide auditability. These are some fundamental concepts of a general workflow that also apply to AI workflows. One common architectural pattern that you will see in enterprise AI systems is fan out and fan in. Fan out is splitting the work into multiple independent tasks that can be run in parallel. In this example, the user asks a question about renewable energy. Rather than performing a single search, the workflow fans out three retrieval tasks for searching enterprise documents, relevant examples, and companies' policies or guidelines. Since each of these three retrievals are independent, they can execute in parallel, reducing the overall latency. Once the parallel tasks are complete, workflow can fan in, which means combine the results into a single context for passing to the large language model. Fan out and fan in is a powerful pattern that improves the performance through parallel execution, and it appears frequently for retrieval, tool execution, validation, and many other enterprise scenarios. Let us walk through an example workflow using a clinical research assistant. Imagine a medical researcher asking a question about treatments for early stage Alzheimer's disease. The first thing system does is to reformulate the question using either a large language model or a rules engine to better represent user's intent. For example, it can expand abbreviations, add keywords such as clinical evidence or mild cognitive impairment so that system can fully retrieve relevant context which is required for answering this question. The system then retrieves the context by searching knowledge sources, which in this case could be clinical guidelines, PubMed articles, treatment protocols, etc. The large language model reads all the retrieved evidence and synthesizes it into a concise answer by comparing the treatment options and explaining why certain therapies are recommended. However, before returning the response to the user, the system applies guardrails where it checks if the medical claims in the final response are supported by the provided context, no accidental patient data is leaked, and answer complies with healthcare policies or safety guidelines. If any of these validations fail, then instead of returning a potentially unsafe answer, a workflow can enter the improve query or context loop. The system might reformulate the search, retrieve additional publications, redact sensitive information, or tighten the instructions given to the model to improve the output. This loop continues till the answer satisfies the quality and safety checks, and once it does, it is returned to the end user. Throughout this workflow, you notice that there are several components that work behind the scenes. For example, knowledge sources can provide trusted information, tools can be executed by making calls to enterprise APIs for retrieving information. State and memory can maintain conversational history. For example, the system can remember that earlier in the session, this researcher was particularly interested in elderly patients or stage 2 clinical trials. So, even in this response, it can try to incorporate those details. The key takeaway here is that large language model is only one step in the workflow. The production grade AI application is an orchestrated pipeline where retrieval, reasoning, validation, tools, memory, and guardrails work together to produce the outcome. And this is what workflows enable. Now that you know what workflows are, you may think, how do I go about designing one? The mental model for designing a generative AI workflow is divided into three phases. The first phase is planning phase, where you should define the business outcome, identify the information that should be maintained in the state throughout that workflow, and also define the constraints or guardrails that you must implement in your workflow. In the second phase, which is the building phase of the workflow, you should decompose the problem into well defined tasks and then design the orchestration flow by deciding which tasks can run in sequence, which should run in parallel, are there any conditional steps, and at which step should we call the large language model. And finally, to operate the workflow, you must plan continuous evaluation, reliability, security, and wherever appropriate, human oversight in this process. A good AI workflow should also have a feedback loop so that it can improve over time based on observations and evaluations. So you can think of workflow development as a life cycle where you plan the business objective, build the orchestration, and then operate it as a reliable production system. Now let us discuss some common frameworks that can be used to implement AI workflows. LangChain is one of the most popular frameworks for building AI applications. It is a modular framework which provides reusable building blocks for connecting the large language model with prompts, retrieval systems, tools, memory, and output processing. For example, you can use Retriever to fetch information from vector stores, an output parser for structuring, validating, or converting the response into the desired format, memory for maintaining conversation history or application state across interactions. However, as applications become more sophisticated and require complex orchestration, such as branching, loops, parallel execution, orchestration frameworks such as LangGraph come into picture. LangGraph is the workflow orchestration framework that builds on top of modular components of LangChain. With LangGraph, you can build graphs of connected tasks with support for branching, loops, conditional edges, retries, and a state that persists across every step. In this example, every rectangular box represents a node which is a unit of work. The edges, which are the arrows between two nodes, define the execution flow from one node to the next. Execution flow can be conditional. For example, since the model's reasoning is not known at the design time, we can have a conditional step that checks if model wants to call a tool or it is ready to give the final response. Depending upon the situation, you can branch to the correct node. So basically, with LangGraph, you can design AI agentic workflows that combine the deterministic flow of the workflows with dynamic reasoning of large language model. While LangChain and LangGraph orchestrate AI reasoning and agent workflows, technologies such as AWS Step Functions and Temporal are designed for durable business orchestration. Often, all three technologies are used together in an enterprise workflow. Step functions can manage long running production workflows that may execute for hours, days, or even weeks while providing enterprise capabilities such as retries, fault recovery, timeouts, compensation, and human in loop coordination. In this example, AWS Step Function orchestrates the business process by coordinating the end to end workflow. It validates the request, invokes business services, handles asynchronous human approvals, persists results, and notifies downstream systems. Most of these steps are not AI, they are standard business operations. When the workflow reaches a step where it requires intelligence, step function invokes the AI agent, and this is where LangGraph comes in. LangGraph orchestrates the AI workflow itself by managing the planning, retrieval, tool execution, and iterative refinement of the overall workflow response. And LangChain provides the reusable components to LangGraph for prompts, LLM integrations, retrievers, tools, etc. So basically, the AWS Step Functions orchestrates the business process. LangGraph orchestrates the AI reasoning and decision making, and LangChain provides reusable AI components that are used by the agent. This layered architecture keeps business logic, AI orchestration, and AI capabilities cleanly separated, making it easy to build, scale, and maintain the enterprise AI application.